We left off yesterday discussing the Burrows-Wheeler transform. So here's a nice picture that concisely shows what it is. So maybe I'll try to leave this up. What is the Burrows-Wheeler transform? Just to get us briefly back on the same page. You take a text. You see this text is written down here or also here. You take all the cyclic shifts. Well, first of all, you put a $sign at the end so that you know where it ends. Then you take all the cyclic shifts and you sort them alphabetically or lexicographically. Then you get this little matrix of characters, and you take the last column. That is the Burrows-Wheeler transform of the original string. And we noticed that this transformation has some cool properties in that if the original string has repeated substrings, for example, the orange ones here, that occur exactly repeated or very similar, then you will also find these grouped together in the Burrows-Wheeler transform, and they will give rise to local clusters of characters, which can be in the form of pure runs, the same character repeated many times. Well, they can be, like in this orange case, local clusters of this space character, but there might be other characters sprinkled in occasionally. And so how we use this in compression is to first apply the Burrows-Wheeler transform to a text T. That gives us this string. And then we went on to take the move to front transformation, which we also discussed last time, to transform that into a sequence of numbers, integers. And you notice that local clusters like this here tend to either go exact repeats, go to runs of zeros, and local clusters lead to small numbers. The example is still a little bit too small to see this in full. But, well, how big's the alphabet in this example? Well, it might be too small to see the effect very pronounced, but you see there's many zeros. We get a couple of 2s and 1s, and we do get some bigger numbers too, but they're only relatively infrequent. So that was the reason why the Burrows-Wheeler transform is great for compression. If you apply it to a text, you take the same characters of the text, you just permute them, shuffle them around, and magically, well, not quite magic, but it's built into the transformation. The resulting text, the transform of the text tends to be much easier to compress with methods we've already seen. Move to front can amplify that even further, and then we can use tricks like run length encoding and Huffman coding to exploit the fact that we see many zeros and many small numbers in this move to front of the BWT of the text. Okay. In the last part on compression and on text transformations, we will talk about how to invert the BWT. We've seen in the last section that the Burrows-Wheeler transform is great in making the redundancy in a text more explicit so that we can exploit it using the chain of applying the BWT to the text, then move to front transformation, and then other methods that we've discussed, Huffman coding, run length encoding. But this is only useful if we can decode the BWT as well. So given the BWT, can we get the original text back? And that's, if you look at the definition, not at all obvious, because the BWT involves sorting. And usually sorting is a destructive process. If you start with a list in some order and then you sort it, there's no way you can get back the information of how the list looked like before. You can try to store that information separately by annotating each element with the index where it was before the sorting, but that's not what the BWT does. So how is it possible that we can invert it? That's what we'll look at next. And it turns out there's a very simple solution that lets you do it. And I'll just show you on an example how it works. And then we'll spend the rest of the video to understand why it works. It's a very interesting algorithm because the fact that it works, and the algorithm is very, very simple. And you'll see in the example, it just works. But the tough part is understanding why. So implementing the algorithm, very simple. Understanding why it's actually correct, a bit more tricky. Okay, here's the magic solution on an example. This is the transformation. That's the BWT of some text, but we don't know the text. The only thing we know is, well, it ended with a $, and it obviously had a couple of A's, one R, one C, a couple of B's, etc. So we know what characters the text is comprised of, how many copies of each character, because that stays the same if you take the BWT. But that seems to be pretty much all we can obviously see from looking at this. So here's the algorithm. Here's what we do. We create an array of pairs. This is written down from top to bottom here. And the pairs consist, well, its pairs consist of two entries. The first one is the rth character in the BWT. So the entry at position R is the rth character in the BWT. And the second is just an index. So we kind of remember where the element was in the BWT. But that's not the same as what I said before with the sorted list, because this is already sorted. This is remembering where it was in the sorted list. But here's the definition. So this is what D looks like. The second component just counts from 0 up to length -1. And here you can read, again, the BWT. So nothing intelligent happened so far. The second step is we sort this list stably after the first entry. So what do I mean by stable sorting? I just mean if there's several A's, I will group together all the A's by sorting. And I will leave the second component intact in the same order as it was here, which is a fancy way of saying you just sort the pairs lexicographically first after the first component, and if that one's the same, you sort it after the second component. I'm stressing this fact that we don't do this because we don't have to. The second component is already sorted, and it is cheaper in terms of the running time to only sort the first component, because that's from the alphabet. We assume that's a small alphabet, or in any case, it's never bigger than the number of characters. So we can do this sorting step in linear time with counting sort, okay? That's another instance where we make use of this fact that we can sort in linear time if the universe is small enough, if we have numbers from roughly the same universe size as the length of the array. Okay, again, we haven't really done anything magic yet. But what we do now is we interpret this new list, which still has indices, but now, of course, because I changed the order, the entry at position 3 no longer has second component 3 as it was before. And now we simply reinterpret this list as a linked list representation for the original text. Namely, the first component gives me the next character, and the second component tells me where to jump to get to the next entry. That's exactly like we use pointers in syncly linked lists. And that gives you the text in the original text order. Let's see it on an example. The first entry in this sorted list necessarily is the $, because we always have that first in the lexicographic order. We define it to be smaller than all the other characters. So this is always the first entry. But what we do in the algorithm is when we arrive at a pair, we write down its character, but in the initial step, we say we're already there, so we don't write the dollar now. Instead, we follow the 3 right away. And that brings us to that position, and we write down A as the first character in the string. Okay, so this first step is a bit, the definition just has to be whenever you go to a new pair, you write down its character. Okay, so we did that. Now, next thing is 7. So we jump to 7, write down the character B. That's the second character in the string, I promise. And we continue. So we jump to 11. That's down there. So next is an R. Now we jump to 4. That gives us another A. Jump to 8 gives us a C. And you see, whenever I enter a new pair, I write down the character here. So I produce the source text from left to right by just following pointers in this list. So let's do that. And one more time. And then at some stage, we enter the first element again. I want to be on that side. At some point, we enter the first pair again, which means we output the dollar now. And that also means we know we're finished. As soon as we reach again the index 0, we're done. And the definition of the BWT guarantees us that we will always walk through this list and at the end return back to the first entry. And here you see the source text was abracadabra. And if you write this down, take all the cyclic shifts or the suffixes and sort them, take the last column, you will find that this is indeed the BWT of abracadabra. That's magic, isn't it? So let's have a look at why this works. Again, the algorithm is very simple to implement. You form these lists, you sort them after the first component, and then you walk through the list as if it was a linked list with pointers. Okay, very simple. Why on earth does that correctly invert the BWT? So first piece of information here is we can always find the dollar character in the BWT. And that means we know where to start. Now here we used sorting to implicitly get the dollar to the first position. But what we needed from the dollar was this 3, which is its position in the BWT. Right? So the first step was just a sneaky way of finding this position of the dollar in the BWT. But we can always do this manually as well if we wanted, because there's only one dollar sign in the BWT, so we can always find the unique position where it is. So that tells you in this sorted sorted list of cyclic shifts, where is the starting row? Because then if you find the dollar in the right-hand side, you know where to get started. Maybe let me show this on the example. So the picture illustrates the second point, but I want to first look at this again. So we find the unique position of the dollar sign in the BWT. And because that's where the dollar is the last symbol, we know that this is the first symbol. So if we jump to, if we take the position where the dollar is, that's the starting row in the sorted list of suffixes, cyclic shifts. The second piece is, so we know where to start now. That's great. Now we need 2 more things. First of all, we need to find in the current row in this list of sorted cyclic shifts, we need to find the first column, the character in the first column. As you've just seen in the example, that was the B, the first letter in the string. So we have to somehow make the jump from the last column to the first. that's part one. So maybe make that green because I'll have more things to draw in a second. And then the second thing we need is now that we have this character in the first row, we want to find that character on the right so that we can then jump back to the front of that row. Okay, so let me illustrate that again. So now I took green for this one. So let's take orange for the second step, green for this step. We know where to start. The green thing says I have to jump to this, to the first column, because I need to know what that character is so that I can output the B. And then the next step is I have to find this B on the right. So I have to find that this is the first letter in the string. So I have to find this one, which is also the first letter in the string. So I somehow have to make this move to the right, okay? Which is illustrated in the picture for the A's, but let's do it step by step here. So this is what I have to do. Now, how can I do this? Switch to green again. How can I get the characters in the first column? Well, that is actually easy. If you look at those guys, these characters in the first column, they are just all the characters in the BWT in sorted order, right? The dollar first, then all the A's, then all the B's, all the N's. That I can obtain by just sorting the BWT as if it was a list of characters. Now, if you go back to the algorithm, we didn't explicitly sort the BWT anywhere, but, well, we sorted these pairs. So here is the same green row of characters in the first column. Okay? So that part's indeed not too hard. We get that by simply sorting the BWT alphabetically. The tricky part is the second thing. We have to make the jump to the right. And in general, there can be many copies of a character A, and many copies of a character A on the right. So how do we know which one matches which? When I went from this B to that B, I kind of used the entire matrix, seeing that this B is the first, so it follows the dollar sign. So I've seen that here it follows the dollar sign, here it follows the dollar sign, so it must be the correct one. This is not something that the algorithm can do because it doesn't have access to the middle columns. It only sees the first column and the last column. We can still do it though, because the relative order of the same characters stays the same. If they're sorted, this is A1, A2, A3, A4, then A1, A2, A3, A4 stay in the same order in the BWT. And the reason for that is this list is sorted lexicographically, so it's sorted by whatever follows the A. And if you take the A to the end, that means you now start with one character later. And if ban was the smallest of the strings that follow an A, it still is smaller than all the other strings following an A, like N and Naban and Naban, Nanaban, etc. Okay? So because this was sorted and the A is the same, the order of what follows these guys stays the same if we take the A away. So the first A in the sorted order here has to map to the first A in the BWT. And that again is something we implicitly did in the algorithm here by keeping track of where these positions are. So we kept for A's, we kept their indices 0, 6, 7, and 8, and 9, and well, that's it. And now if we were at the second A, we know it is actually in row 6. And so we know where to go next. So that that explains how we can how this algorithm actually uses the information of the middle columns that it doesn't explicitly know by using these two facts that we can jump to the left by sorting the characters, and we can jump to the right to the next character, find the corresponding copy in the rightmost column in the BWT by going from the ith occurrence of a character to the ith occurrence of a character. And that's what we do by stably sorting the pairs. It's still a little magic, and I find it very exciting each time I see this, because the definition with the pairs is so simple and so easy to execute, and yet it takes a good deal of thought and caffeine to digest why this actually works and correctly decodes the BWT. That brings me to the end of the BWT section. We now know how to encode and we know how to decode. The running time is linear in both cases, building on on the fact that we know that we can sort suffixes in linear time. But remember that this is a fairly complicated algorithm. We can do it in linear time, but the algorithm needed, well, it was the DC3 algorithm with these 3 steps, and there was this alphabet explosion. We had to rank reduce the alphabet. We had to do a fancy merging method, etc., etc. For decoding, the only thing we need is counting sort. So that's an exercise for a first-year programming class. So again, we have a method. We have this observation that we've made for many of the other compression methods. Decoding is usually simpler and faster, and that's also true for the BWT. Computing the inverse BWT is very simple and fast, even though conceptually it looks very challenging to do. And encoding seems more complicated, even though in theta notation there's no difference. The downsides of BWT is exactly this suffix sorting. It is slower than other methods, simpler methods. And we also need the entire text available. We cannot do this streaming unless we break the text into blocks, which is of course an option. But the big positive thing, and this should be, like, I should have drawn the icon a bit bigger, it is the culmination of this long unit on compression to have explained all parts of this pipeline that give you the best possible compression that we know of for typical English language text and other similar types of data sources. By combining things in this way, and you can look up the bzip program to see more details. So the BWT is on the slower end of the spectrum, but gives you the best compression ratio that we have seen. And that concludes the Unit 7 on compression methods. Here's again, in a nutshell, the methods that we've seen, the non-trivial ones. We have Huffman coding, which is fixed to variable. We have single characters are encoded using variable length code words. It's best possible in this case if you insist on encoding each character in isolation. Then we've seen run length encoding, which can get really great compression in very extreme cases. But in isolation is not very strong, but is a valuable part of the pipeline. L'impulsive Welsh, a fast but effective method if you have repeated substrings, and used variable to fixed encoding. And then the 2 text transforms, the move to front to transform simple repetition into redundancy of the characters, and then finally the BWT that allows to group things by context and thereby greatly amplify the compression that we can achieve.